Our second speaker today is Colin Wang.
You can just call me Colin.
And he will present CharXiv charting graphs in realistic chart understanding in multimodal LLMs. So Colin is a second-year master student advised by Dante, and he earned his Bachelor of Science in Data Science and a Bachelor of Arts in Cognitive Science from UCSD, and he's also a 2025 Siebel Scholar. Please give it away for Colin.
Okay. Well, you didn't do the second part, but anyways. Hi everyone, my name is Colin Wang. Today I will be introducing you our latest not preprint. Actually, it was just accepted this morning in yours. So it's in yours. Okay, charting gaps in realistic chart understanding in multimodal large language models. We have 11 authors from the PLI. And then we have one author from University of Wisconsin Medicine, who is actually the first author of LAVA. And we also have one, I think it's an exchange student in our PI, who's from the University of Hong Kong. So multimodal large language models are very hot nowadays, and almost all the models have to evaluate on some chart understanding evaluations before they actually get to meet the public. When Cloud 3.5 Sonnet was released, it was actually tested on 5 multimodal benchmarks, so 2 of which are heavily based on chart understanding. So one of it is CharQA, with exclusively chart question answering, and the other one is MathVista, where more than 20% of the samples are about understanding the charts. So given its performance over 90% on CharQA and 68% on MathVista, can we really say that they understand charts? In the next section, I will prove you that these numbers represent an over-optimistic measure of progress. So I will start with the claim. Existing benchmarks, they oversimplify chart understanding. As background check, our MathVista is a multimodal math reasoning evaluation suite. 20% of the samples came from those benchmarks, DVQA, Plot QA, Figure QA, and Chart QA. This evaluation suite gets very popular recently, and Chart QA is often used as a standalone benchmark to test chart understanding. But if you look at the chart sample, they're either synthetically or picked up from a single source of basically homogeneous charts you see. So DVQA is fully synthetic. All of them are just bar charts. Plot QA is very simple. Figure QA is also very simple. The styles are even very similar. And Chart QA is just picked from several websites that all use the same style. So let's begin with a fact. At least a fact in open source, multimodal large language models. So they are often trained on existing chart datasets. And that means that all the previous datasets, such as Figure QA, DVQA, Plot QA, Chart QA, they are part of the instruction tuning dataset to train these models. And while they do not use the test set to train it, which is otherwise obviously wrong, they actually probably did not realize that the synthetic nature of this data set, where in-domain training can lead to significant boost on in-domain evaluation. But what if samples no longer look like what's being trained on? That's actually the motivation of CharXiv. So from that point, we actually started building 2 sets of chart question answering samples from 184 existing chart QA samples in MathVista across Figure QA, DVQA, Chart QA. So in short, we have a modified chart set where we keep all the questions in 184 samples the same. Okay, so it cannot be exactly the same, but it's essentially the same type of questions. For example, if the original question asks if something is greater than something, then we also ask the same question. And now we also collect charts from archive papers that can be asked with the same type of questions. So basically now we have this kind of modified chart set. Okay. And then in the modified question set, we basically modify the questions and keep the charts untouched. Note that there are different questions, but they're still contextualized within the charts. And in both settings, we ensure an equal amount of yes/no answers as well as third number answers. And all the samples in the 2 sets are annotated by ourselves. Human annotated. And once we have the modified chart set and the modified question set, we compare the performance change when models are evaluated on this set with respect to the original sets. And here is what we found. Okay, so we selected a range of open source models where they stated that these models are basically trained on the training set of existing chart understanding datasets, and we compare their performance with proprietary models. And as you can see from the charts, all 4 proprietary models, I believe it's Cloud 3 Opus, Recard Core, GB4V, and GB4O. They closely stay along the diagonal line, meaning that they're just probably fine, right? They get a similar performance across modified questions, original questions, modified charts, and original charts. But if you look at the open source models, they all get exploded. We have seen the most extreme case happening to the Sphinx V2 model. The accuracy just dropped from 60-ish to less than 30 once only the questions are changed. Similar but less severe patterns are observed in all the open source models. This basically demonstrates that in-domain evaluation leads to an over-optimistic measure of progress, and it sparks us to propose the CharXiv benchmark, which actually aims to fix this in-domain evaluation problem. So as a wrap up from the last section and the introduction to this section, CharXiv represents the first realistic, diverse, and challenging chart understanding benchmark. That being said, all the charts and questions are made by people from the real world. And because they're made by different people, the charts are naturally diverse, and so as the questions. And finally, all the charts are collected from recent papers from arXiv, which means that the charts themselves are usually, for recent papers and just naturally challenging, right? And with challenging charts, we naturally ask challenging questions. And know that all the questions are labeled with our in-house labelers, which are just mostly graduate students from Princeton. Instead, we didn't hire any Turkers because we don't really trust them nowadays. So let's unfold the CharXiv and begin now, like how we handcraft and handpick the charts. So for this, we actually decompose it into 4 steps. In the first step, we perform like data pre-processing, where we bulk download hundreds of millions of arXiv source files from arXiv's establishment. And in the end, we decided to only go with the figures from 2020 to 2023, as we found the charts from like earlier years, they're not as visually diverse as in more recent years. So we included all the subjects that are from arXiv, which are statistics, quantitative finance, biology, physics, mathematics, etc., etc. For all the figures within this years and subject, we use LaTeX parsers. Monjo wrote that part, and we actually found out all the figures used in the paper, and then we re-render those vector-based vectors such as PDF and EPS. We re-render them into high-resolution standard JPEG files. We resize them to have a longer set of 1024 and padding the rest, white color. We choose this resolution because lots of the charts from arXiv, they contain subplots and charts that can be unreadable if it's rendered in a resolution such as like 336. That's usually the standard resolution for VLT models. For all the JPEG we render, we use a Seglit model to do semantic pre-filtering. For those who don't know what the model is, you can think of it as one capable of finding semantically similar figures from an anchor set of figures. So if you use this kind of anchor figures, and you can use this Seglit model as a filter to select figures or charts, right? So here we simply use the chart samples in MathVista as the anchor set of figures. We take the average image embedding of this chart and keep all the figures from our render archive images with a frequency of 0.65. And this number is important, neither too high or too low, because if you set it too high, say 0.8, all the charts that are selected looks very similar to what we've seen in MathVista. And if you set it too low, it's likely that it just not do any pre-filtering at all.
So you basically pre-filter it based on the LaTeX, like for the charts that you extracted.
No. So they usually attach their PDF files and EPS files for charts, because usually you use those files to use a matplotlib to generate those figures. Yeah. We actually use a renderer to convert those PDF vector-based PDF files, PDF-based figures, to the JPEG file raster.
Oh, I see. So you take the PDF directly. You don't really.
We take the PDF version of the figure. Yeah, and we render it into JPEG.
So yeah, I can see that not having a high failure rate, because if you recompile from LaTeX.
Yeah, if you recompile, I think it's more.
Bias.
Yes. So after pre-filtering, we sample 750 figures from each and subject. We actually start involving human intelligence, and we ask the annotator to choose the best part from a set of 10 figures at a time. So this is actually an example in our annotation. So we ask the annotator to prioritize the clarity and diversity of the chart. That's the first priority, okay? So after step 3, we ensure that each year and subject contain roughly the same number of charts, which is like 75. And at this point, we'll perform the final data processing, where we apply a model-based approach. So we deduplicate charts based on greater than or equal to 0.95 of pairwise equivalent similarity from Seglit image features. Sometimes we realize that in the same paper you can have like 2 figures that look really similar. They are just like for different experiments, right? So we basically did some semantic-based deduplications, and finally we did a full pass of human inspection to catch any non-charts and blurry charts that were accidentally selected by the chart selection annotator. And after this step, we ended up having 23 charts. It's a weird number, but it's fine because I graduated in 2023 from my undergrad, so I use the 23. Now for each chart, we pair it with descriptive questions. We actually realized that no matter how visually diverse the charts are, they just share common elements. And you can ask the same question to many different charts with no compatibility issues at all. And to this end, we inspected a lot of them and come up with 19 unique questions. I want to say a kudos to Lucy, who helped a lot on thinking of like what are the unique elements are. The basically covered all the property of the charts. For example, the title, x-axis label, y-axis label, text. These are some basic information that we want to ensure that the model learns some basic enumeration and comparisons. We also have questions like, the max value and the range of the continuous legend or consecutive differences between the text, or enumerate all the discrete labels. After that, there are more complicated but basic questions in patterns, such as line intersection, trend of data, as well as subplot layouts, which we term as pattern recognition. And finally, we have like counting, where we ask model to count at different granularities from labels to lines to subplots. Oh, and for compositionality, we ask the model to count the tick labels across axes. And it turns out that this question is very important as part of our analysis. So stay tuned. I will talk about this later. Concretely, I will show you one contextualized descriptive question. For example, for this, we ask the subplot at row 1, column 5. This one, right? Which is obviously the top right one. What is the rightmost label take on the x-axis? I think from a Q1 perspective, it's a bit small, but from a Q1 perspective, it's concept. But all the models basically said like strap concept. I think they realized that they probably merged these two labels together, but in fact, it's just poorly designed. They belong to different bars. Models think that they're just from the same labels, the same single unit of label. So now this model can get it right, even including GB4O. So I mean, like even in this very simple diagnostic questions, the strongest model can still make very stupid simple mistakes.
Sorry, what changed? I didn't quite get it.
This one? Oh, sorry, it's a bit small.
Oh, I see. The top answer is
close to
correct.
each other. Yes.
The top answer is correct.
Oh, none of the answers are correct.
Sorry, all of them are correct.
All of them are wrong.
Is it possible I can render you?
Oh, I see. Row 1 and column 5. Got it. Okay.
Yeah, it targets this chart, but it thinks that this belongs to the same label. Okay, so they actually belong to different bars, but they're just the tags are very close to each other, and they think that they belong to this bar.
Is it possible rendering?
It's not rendering. I mean, it could be the author, like the author who make the plot issue, but I think in terms of render, we have the high resolution, and if humans can know that they're from different labels, I think the model shouldn't make the same mistake. Yeah. And one more characteristic I want to show is that we have like intentionally 25% of the questions that are unanswerable, such as asking the number of lines in a bar chart. Maybe you can say that this bar is a line, but I don't really think so. Know that we have like proper instructions to the model to say not applicable for unanswerable cases. Usually you would just say not applicable to a bar chart if it contains any lines. But yeah, in 4 out of 6 models shown here, they all pretend that there are some lines in this plot, in this bar plot, which kind of makes sense. Yeah.
Yeah, it kind of makes sense.
But seriously, there's no line on the chart based on the definition because it's a bar chart, right? So GB4 answer not applicable, but some models just say the plot contains 4 lines. I don't know what the 4 lines are. Maybe it's referring to the legend. But obviously, I don't think
So-
it's. Yes.
But this question is ambiguous. Like lines means what? What does line mean in the context of plot? I see plenty of lines. Straight lines.
There are some follow-up instructions. Like if you don't see clearly, like clear lines from a chart perspective, like chart data.
Yeah, so that's what I'm
you should
saying.
answer not applicable.
Yeah.
So there are still models saying not applicable, but lots of models just say, like give you some numbers like 4 or 10 or something.
But was this automatically generated? Is this one of your things? Like,
This is one of the template-based questions because
Yeah.
they're applied to different charts. So now after this more complicated descriptive questions, we also construct reasoning questions to truly challenge these models. So if you consider reasoning questions as challenges to these models, the descriptive questions are just really easy. So the core principle of reasoning question is that each chart represents a unique story as a standalone event. So we have to hand draft each individual question tailored to the content of the chart. And we actually do it without access to any of the captions or paragraphs that it originally accompanies. That way we prevents from any data leakage, right? And to do this, we start from a source chart, and then we give this chart to the GB4V model to generate some sample QAs following a predefined instructions. And from there, we release the source chart and all the sample QAs to our excellent graduate student annotators. And now they face 4 options. It's possible that one of the QAs are really good. The answer is accidentally correct. GB4 made a lot of mistakes. in which case they just put it as a final QA. In some cases, annotator find a really good questions with the wrong answer, and this results in a multiplication of the answer with the same question. Sometimes like if you can find good question and good or bad answer, this only account for like 20% of the QA sources. Another 20% of QA sources happen when the annotator thinks that a question is interesting only if it's asking for some other potentially more challenging variables. In which case they just multiply both the question and answer. And in the remaining 60% of the time, the annotator believes that the GPT did a very bad job and end up writing their own questions and answers. So for each answer the annotator crafted, they need to ensure that the answer are in 4 types: text in chart, text in general, number in chart, and number in general, which we'll discuss what concretely mean. Basically, text in chart means that it's kind of piece of text that are from the chart itself, like what is the label of the y-axis in the subplot, and there are a lot of conditions. Where the blue dots form the smallest clusters. So you need to figure out that it's this subplot, and then you need to figure out where is the y-axis. It's here. Okay, so it looks blurry here, but I can guarantee that if you see the actual figure, it looks very clear to humans. Text in general mostly asks for trends, like whether it's increase or decrease, but this one is a bit tricky, running to the nearest hundreds. What is the first frequency where the theory curve achieves approximately the same Raman intensity as the value achieved by the experiment curve at this. A lot of models make mistakes. I think this question was annotated by Alexi, was graduated from our postdoc program. Number in chart. How many false negative detections are there for this in the X dark data set?
How do you evaluate the correctness of the answer?
Okay, we have the number in chart and number in general. Those are like you need to ground the number existing in the chart, or just like number in chart is mostly counting. Next slide. Now let's talk about how the responses are validated. So because CharXiv sources charts from like scientific domains, sometimes like a lot of charts contain equations and math symbols, and some models like to give like UTF alpha character, and some models just give LaTeX grammar to represent it. And this means that we can't usually do exact match. But we talk about the fact that we have specified a fixed type of answers, and we actually make all the answers easily verifiable via LLMs, where we actually design in-context learning examples and grading instructions for each answer type. And then during the response grading, we just retrieve the relevant ICL examples, in-context learning examples, and instructions along with the question. This is pretty similar to MathVista, where we provide with the reference answer provided human and the model's response, and we ask GPT-4 to basically assign a binary score, whether it's correct or not correct. We don't offer partial correctness because many recent work indicated that such design can cause evaluation to go beyond the factuality. Sometimes maybe the style matters. Sometimes maybe other things we don't know that matter, right? So there's an interesting point where one of our reviewers suggested us doing a manual evaluation on this automatic evaluation because you're concerned maybe GPT-4 is not 100% correct. And our result actually shows that they match 98.5% of the time, which is quite high. And the F1 score on matches.
You have 5 minutes.
Yeah, that's okay.
Are you worried about any leakage, like someone could try to reproduce this pipeline and generate the answers themselves and kind of like game the benchmark? Like, are you worried about that leakage?
What kind of leakage?
Like, I've seen someone could generate the answers, like the correct answers using exactly the pipeline that you described.
Yes, but if they get a very high and potentially suspicious score, I guess someone will want to reproduce it with their models. I guess it's fine, right? Okay. As of now, CharXiv evaluated more than 40 multimodal large language models internally evaluated by companies. They're also currently internally evaluated by companies developing proprietary models. I won't say which companies, but I guess we can directly jump to results and takeaways, given we got a picture of how charts are selected and how questions are constructed and how answers are validated. So first of all the models struggle with reasoning questions. We see 20 points gap between the leading model and the human expert. And open source models, the highest one is, I think it's interval 276, but it's a 70B model based on Llama. From there, we see that the vast majority of all models cannot even achieve a score above 30, which translates to that they incorrectly answer 70% of the reasoning questions. Note that the HPA random guesses will incorrectly answer 90% of the questions as a reference. So it's not a lot higher than just randomly guessing.
Green are just open source.
Yeah, green are open weight actually. I just refer to open source here. Similar trends for descriptive questions, but the gap between the closed source models or proprietary models and humans are smaller. One interesting thing we see is that if you carefully check the above 2 slides, you can realize that the ranking pattern appears very similar. So with our post analysis after our preprint, we actually found something very interesting, where we found a 0.89 correlation between the performance of descriptive reasoning question when we fit a linear regression with this formula, 0.52 times your descriptive score minus 0.83, you will roughly get your reasoning score. This is very interesting, but it's also kind of intuitive because many models come up with zero-shot chain of thought. And if they make mistakes in any intermediate state, it's likely that they compound the mistake later and result in a wrong answer. This is especially true for reasoning questions. And another direct question out of this linear regression is that it seems that the reasoning score is the upper bounded at 51 points, assuming model achieves a 100% descriptive score. So we do believe that something is happening that can either bump or drag down the performance on reasoning questions holistically, that are other than the descriptive questions. And again, we also found that zero-shot chain of thought may not actually always be helpful. We see stronger model performance improves with more reasoning, while weaker model performance can actually degrade with more reasoning. So we conjecture that the perceptual errors made in the chain of thought can compound in the chain, which will lead to a wrong conclusion. And finally, we see some of the strongest models whose performance doesn't really vary by the length of reasoning for reasoning questions on CharXiv, such as GPT-4, which is on the top. Finally, I think we have 2 slides left. Our fine-grained analysis on descriptive questions, we found the vast majority of models fail to perform sufficiently above random chance, but the task itself is highly compositional and rarely appear in nature, right? So one specific descriptive question is to ask models to count the number of labeled ticks on both x and y axis. So like this, 1, 2, 3, 4, 5, etc. And we see a lot of humans achieve like almost perfect score, which is kind of very intuitive, given how easy the task is. A lot of models cannot even get it right for even 10% of the time. On the other hand, we do see that there might be a scaling effect that larger models tend to do well on this task, or models that may have been distilled from larger models, totally my conjecture, such as GPT-4 mini. I think that a Turing test based on this question will make human models distinguishable by a lot if you compare their performance gap.
Do you know how robust this is? Like, I think how much of it depends on the prompt? Like, if you kind of into the model in the prompt.
That is a good question. We didn't do any ablations on that, but we might be able to find a pattern there.
Yeah, we're doing something similar.
Like prompt tuning or something.
Yeah, exactly.
Weak models failing to identify unanswerable questions. This is the first that we discovered because previous work they didn't, as if model rejects the answer if elements don't exist in the chart. We showed in the example before. From this, I guess a possible direction would be to reduce like LLM hallucination with a bunch of models and use their disagreement as a signal for potential hallucination reductions. But we'll just leave this as a future work. So you can see that different models make different types of mistakes in unanswerable questions. And lastly, pretty intuitive, we see that both reading descriptive questions degrade when there are more subplots and more pronounced for open source models. The reason that it's intuitive is because open source models, we know their training data from their technical report, and we know that their data don't contain charts with multiple subplots. And unfortunately, the chart, they just all involve single plot. So from the plot itself, we see the models still fail. I mean, they still generalize to multiple subplots, but it's not a robust generalization. So there's still like this for performance drop when there are more and more subplots involved in a single chart. And this happens for both open source and closed source models. Proprietary or closed source models are just more robust, I think, than open source models. So summarizing everything is my final takeaways. I think good evaluations need to be diverse, realistic, and curated by human if possible. So unlike CharQA, where the strongest model achieved like 90% plus accuracy, strongest model can only achieve 60% accuracy on CharXiv. Second place only achieved like less than half. So CharXiv revealed lots of shortcomings and insights of multimodal large language models in chart understanding, including that reasoning capability in chart highly correlates with descriptive capabilities. Multimodal zero-shot chain of thought can sometimes be harmful if there are a lot of perception issues.
Colin?
Yes, last.
Yeah,
Okay, we can.
Maybe quickly wrap up.
Models struggle with questions that are very easy to humans. Models hallucinate on unanswerable questions in chart understanding. And finally, model capabilities degrade with number of subplots. And that is the end of my talk. Thank you.